and welcome to today's lesson, which is on independent events. So independent events is a part of probability, and it's worth mentioning what an independent events are. So two events are said to be independent if one thing happening does not have any effect on the other thing happening. And it means that when you want the probability of both of these things happening, then we multiply. Okay? So just to make sure that's really clear, the probability, let's say, what's the probability of it raining tomorrow, and the probability that I will eat some crisps. They're independent events, and if I wanted the probability of both things happening, then I'd multiply. Okay, so let's have a little look at this first question here. So there's a few different ways we can represent independent events. We can represent them as tree diagrams. We can just think about them with all the different outcomes. But first of all, we're going to have a little look at some tree diagrams. Okay, so Tom and Sam each take a driving test. The probability that Tom will pass the driving test is equal to 0.8, and the probability that Sam will pass his driving test is equal to 0.6. First of all, complete the tree diagram. So let's get this one down as example 1 in our book. Now, the first thing that's worth noting is that with trees, the branches always sum to 1. So this pair of branches here will sum to 1, which it comes from the mutually exclusive events part that we had. So here if we've got this, okay, and we've got pass and fail, and this is for Tom, because they've already labelled it for you, and then we've got Sam, and we've got pass, and we've got fail, and again this one here, pass and fail. Then what we do here is we can fill in these from what we've been told. So the probability of Tom passing is equal to 0.8, which means the probability of him failing is the other way round. So 1 minus that, which is equal to 0.2. So we can fill that in. So with this one here, the probability that Sam passes, it says, is equal to 0.6. So that means the probability he fails is going to be 1 minus that, which is equal to 0.4. So we can fill in straight away all of these ones here. So what we've used there is we've used the fact that these are mutually exclusive. Okay, so this here, the probability of passing and failing, you can't pass and fail at the same time, so it must sum to 1. Now, the next thing we need to think about is the fact that these two events are independent. Okay, so independent events means that the probability of Tom passing and the probability of Sam passing is going to be 0.8 times by 0.6. So it's worth now showing. Now, whenever you do a probability tree diagram, they don't tell you to do this part, but it's always worth doing it because it does make life easier for you. So if I want the probability of pass and pass, okay, that's going to be equal to 0.8 times by 0.6. So that's what I'm saying, the probability of independent events we multiply. So 0.8 times by 0.6 is equal to 0.48. So the probability that they both pass is equal to 0.48. So what's the probability that Tom passes but Sam fails? Well, that's equal to 0.8 times 0.4 in this case. So 0.8 times by 0.4. So 0.8 times by 0.4, which is equal to 0.32. So pass, fail is going to be equal to this one. Okay, so then what's the probability he fails then passes? So the probability that Tom fails and Sam passes, again, these are both independent events, so we multiply when we've got independent events. So it's 0.2 times by 0.6, which is equal to 0.2 times by 0.6, which is equal to 0.12. Brilliant. Put a line there so you can see that these are different. And the last one, what's the probability that they both fail? Well, that's going to be equal to 0.2 times by 0.4. So 0.2 times by 0.4, which is equal to 0.08. Okay, so we've completed our tree diagram, And we've completed our probabilities of independent events, so we can start thinking about the next stage, so part B. So part B says, work out the probability that both Tom and Sam will pass the test. Well, we've already worked that out, haven't we, here? So the probability that Tom will pass and Sam will pass is 0.8 times by 0.6, which is equal to 0.48. So part B, and you can write it like this if you want. So the probability that Tom and Sam pass is equal to 0.8. I'm just doing it again. We don't have to do this. 0.8 times by 0.6, which is equal to 0.43. Sorry, 48. Brilliant. So that's that one there. That's part B. So the next question says, work out the probability that only one of them will pass. Well, now this one here is a little bit trickier. And the reason this one's a little bit trickier is because there's more than one occasion that this happens. So for part C, the probability that only one of them will pass, well, there's two different options for this. It's either Tom passes and Sam fails, okay, because it says only one of them passes, or Tom fails and Sam passes, okay? So your two different options are Tom pass and Sam fail, okay, which we've already worked out. Tom pass, Sam fail is equal to 0.32. The other way round is that the probability that Sam fails and Tom passes, which is equal to, so it's not the other way round, so it should be Tom fails and Sam passes. That's the same way around. Tom fails, Sam passes. So Tom fails times Sam passes is equal to 0.12. So 0.2 times by 0.6. So the probability of both of these things happening. Now these are mutually exclusive events, so we can add these together because they both can't happen at the same time. So this is equal to part C, 0.32 plus 0.12, which is equal to 0.44. So the probability that only one of them passes is equal to 0.44. You can even put, if you want, probability only one pass is equal to 0.44. Super. Okay, so let's just be really clear with this. We've got our probability tree diagram, and this is a way of representing all of those independent and mutually exclusive events. Okay, so we've got Tom passing, which is 0.8, and the probability fails is 0.2. We've got Sam passing, we knew was 0.6, so the probability fails is 0.4. And we can use this tree to work out the probability of the independent events by timesing them. So the probability of them passing is 0.8 times 0.6. The probability of Tom passing and Sam fails is now 0.8 times 0.4. The probability that Tom fails and Sam passes is 0.2 times 0.6. And the probability that Tom fails and Sam fails is 0.2 times 0.4. Now the tricky part was this one here, part C. And notice that that was worth 3 marks. So it says here, work out the probability that only one of them will pass the driving test. Well, there's actually 2 times that this comes up. It's this one here and this one here. Okay, so the probability that Tom passes and Sam fails, and the probability that Tom fails and Sam passes. So we work out both of those probabilities, which we've already worked out up here. And then because we want the probability of both of these things happening, we need to add these together. Okay, super. So, let's have a go at the next one. Okay, so what I'm going to suggest is, if you feel confident, pause and have a go at the next one yourself. So I'll get it up for you so you can see it. So pause now and have a little go at this one. Okay, so I'm going to go through it now anyway. So let's have a little look at this one together. Okay, so Louise makes a spinner. The spinner can only land on red or green. The probability the spinner will land on green is 0.7. Louise spins the spinner twice. Complete the probability tree diagram. So our first part here was to complete that probability tree diagram. So let's have a go at this one. This is example 2. I think we should be alright with this one. So we've got two spins. We've got the first spin and we've got the second spin. Okay, and we've got green and we've got red, green, red, green, red. And it says the probability of landing on green is equal to 0.7. So the probability of landing on red is equal to 0.3. The probability of landing on green is still 0.7. So the probability of landing on red is 0.3. So there we've got our probability tree, and this is the first spin, and this is the second spin. Okay. Now the question says, so we've done that part. We've completed the probability tree, and we get 2 marks for that. So the next part, this is worth 3 marks. So this is actually worth more than what we did before. This says work out the probability that the spinner lands on 2 different colours. Well, there's 2 times that this happens. It's either when it's, so green and green is the same colour, so that's not right. Red and red is not right. We're looking at when it's green and red, or when it's red and then green. So we're looking at the probability of it being green and red, or the probability of it being red and green. Now remember, these 2 events are independent, which means that I need to multiply them, okay? Because the first spin, doesn't matter what I get on the first spin, it doesn't have any impact on the second spin. So to work out the probability of it being green and red, it's going to be equal to 0.7 times by 0.3. Do it on the calculator if you want, or you can do it in your head. So 0.7 times by 0.3 is equal to 0.21. Brilliant. And the probability of being red and green is going to be 0.3 times 0.7, which is equal to 0.3 times 0.7, which is equal to 0.21 again. Brilliant. Super. So we've worked out the probability of getting both of these. So where we worked out both the probabilities of being different colours, which is green and red and green. They're the 2 options. Now we need to work out the probability of both of these things happening. So we do that by adding these together. Okay. So here we're looking at the fact these are mutually exclusive. So we can say the word "or" if you want. What's the probability of getting green and red, or the probability of getting red and green? So it's going to be equal to, so the probability of the spinner landing on different colours is equal to 0.21 plus 0.21, which is equal to 0.42. Brilliant. Super. So this here, now take note, we're not using green and green because that's the same colour. We're not using red and red. The time that it happens is this one. But I've got to find out both the probabilities and then add them together. Okay. So I've got another example here. Brilliant. Just check that. Super. Perfect. So this one here is a little bit different. We've been looking at decimals so far, but now we're going to be having a look at fractions. So if you want to have a little go at this one yourself, you can. I'm going to go through this one straight away because it's a little bit different to the ones we've already done. So this one here says Samina has a round pencil case and a square pencil case. There are 4 blue pens and 3 red pens in the round pencil case, and there are 3 blue pens and 5 red pens in the square pencil case. Okay, Samina takes 1 random pen out from each pencil case. Complete the probability tree diagram. So with this one here, the first thing you need to do is to draw our tree diagram and complete it. So let's draw our trees first. Remember, these trees are independent, so they sum together. So we've got this one here, and this is going to be our round pencil case. Now, what are the different options? We've got blue, and we've got red. Okay, and then our circular pencil case. Is it circular? So that was round, and then we've got, the square pencil case. Which is, again, you've got blue and red. So blue and red. Blue and red. Super. Now, we're dealing with fractions this time. So what's the probability of me getting a blue pen? Well, the probability of getting a blue pen is equal to 4 out of, how many pens are in that? Well, it's 4 plus 3, which is 7. So 4 out of 7. So then what's the probability of getting a red pen? Well, the probability of getting a red pen is going to be 3 out of 7. Brilliant. Okay, looking at the square pencil case, what's the probability of getting a blue pen from the square pencil case? Well, that's going to be equal to, there's 3 blue pens there out of a total of 8, so it's going to be 3 out of 8. And getting a red pen is going to be equal to 5 out of 8. So 3 out of 8 and 5 out of 8. Super. So that's our probability tree diagram completed. So the next question says, Samina has a round pencil case and a square pencil case. Work out the probability that both pens are red. So looking at this one here, the probability of both pens are red follows this route down here. So it's the probability of getting red and red. So part B, this was part A, of getting red and then red is equal to the probability of getting red and red, which is equal to 3 over 7 times by 5 over 8. We just times these fractions. Remember, with fractions we times the top times the bottom. So 3 times by 5 is 15. 7 times by 8 is equal to 2. So 8, 16, 24, 32, 40, 48, 56. Brilliant. So over 56. And that's it. Okay. So 15 over 56. And the probability of red and red. We could have done our probabilities here, but I've decided not to with this one because it's only got this part. We're only working out this one. Okay. If it had said what's the probability of getting 2 different colours, then we'd need both of these options. Okay, which is a little bit different. Okay, so let's move on from this. So at the moment we've been looking at probability tree diagrams. So the next thing I wanted to look at is looking at independent events not using a tree diagram. So this is where they get a little bit trickier. So Fred throws a fair dice 3 times. Work out the probability that Fred will not get any 6s. Okay, so it's definitely worth getting this one in your notes. This one here is example 4, I believe. Example 4. Now, we don't always need to work out the use a tree diagram. Sometimes we can just work out one of the events and then times them, because we know that, remember, when events are independent, we multiply them. Okay, so Fred throws a fair dice 3 times. So he's thrown the dice 3 times. Work out the probability that Fred will not get any 6s. So first of all, let's think about the probability of not getting 6. So the probability of not getting 6 is equal to, well, the probability of getting 6 is 1 out of 6, because there's 1 6 on the dice out of the 6. The probability of not getting a 6 is equal to, well, which ones are not 6? 1, 2, 3, 4, 5. So it's equal to 5 out of 6. So the probability of not getting a 6 is 5 out of 6. Brilliant. So the question says that Fred throws the dice 3 times. Work out the probability that he will not get any 6s on those 3 attempts. Now, a lot of people see this and times it by 3, but that's wrong. Okay? What we're doing here is we're saying on the first throw, he's not getting it, which is, we know we want the probability of that, which is equal to 5 out of 6. So that's our first throw, if you want to write it down. And then on our second throw, we want him to not get a 6, which is equal to 5 out of 6. Remember that these events are independent because the first throw has no effect on the second throw. So we times these together. And then on the third throw, we want him to not get a 6 again. So it's going to be equal to 5 over 6 again, like so. So it's the probability of not getting it on the first one, times by the probability of not getting it on the second one, times by the probability of not getting it on the third one. So then we can do it in our calculator. We could do this using powers if you want. So some people like to go 5 to the 6 all cubed, because when we time them together we cube them. But we don't need to worry too much about that. 5 over 6 times by 5 over 6 times by 5 over 6. I wish I'd done the cube now, probably would have been quicker. Is equal to 125 over 216. So that's the probability of him not getting any 6s on those 3 throws. Remember, independent means that we multiply. So the probability of this happening and the probability of this happening, we multiply them together. Multiply here. Super. So let's just check that answer. 125 over 116. Super. Okay, let's have a look at another one. So this one here is a little bit trickier, and I'll tell you why for the next one. So the probability that any piece of buttered toast will land buttered side down when it's dropped is equal to 0.62. Two pieces of buttered toast are dropped, one after the other. Calculate the probability that exactly one of the buttered toast will land buttered side down. Now we could, if we wanted to, draw a tree diagram for this, but I want to try and stay away from that, just with this case, and I want us to try and think about all the different options that we could have. So, the different options are the fact that, well, it's either going to be butter side down or it's going to be not. So let's go B and N. So the options are for 2, it's either going to be both buttered side down, which is B and B. It's either going to be one buttered side down and the other one not. Okay, so this is our first piece of bread and second piece of bread, or toast should I say. The other option is that the first one does not land buttered side down, but the second one does. And then the final option is the probability that they both do not land buttered side down. Now, we know that the probability of landing buttered side down, so the probability of buttered side down is equal to 0.62. We know, so which case, because that's a mutually exclusive event, we know the probability of not landing buttered side down is equal to 1 minus that, 1 minus 0.62, which is equal to 0.38. Okay, so next up, we need to think about what the question's actually asking. Okay, so it says calculate the probability that one piece of buttered toast will land buttered side down. Now it doesn't say here calculate the probability that at least one. It just says 1. So the options for buttered side down, just one, is going to be that it's buttered side down and then not a buttered side down. And then it's going to be not buttered side down and then buttered side down. It feels like I keep saying buttered side down. So what are the probabilities of having one that lands buttered side down and then one that doesn't? Well, that's going to be equal to 0.62 times by 0.38. Brilliant. Okay. Then we need to work out the probability that it doesn't land buttered side down, which is equal to 0.38, times by the probability that it does, which is equal to 0.62. Okay, so there's actually 2 options for this, and you've got to consider all the options so we can think about which ones we want. So, with this one here, the first one is going to be equal to 0.262 times by 0.38, which is equal to 0.2356. It's going to be exactly the same for that one, isn't it? 0.2356. So the probability of both these things happening is equal to these added together. So it's going to be equal to 0.2356 plus 0.2356, which is equal to 0.4712. So the probability that exactly one piece of buttered toast will land butter side down is equal to this. Because it says exactly one. So we can't include this one because that's when they both land butter side down. And we can't include this one because neither of them land butter side down. So it's just these middle 2 here. Notice that we're starting to come away from that probability tree diagram now. Okay, so we're getting that little bit trickier. Okay, so that was that question. So let's just check that. Super, perfect. So one last question here now. So Fred throws a fair dice 3 times. work out the probability that Fred will get exactly 1/6. Okay, so we need to really think about this. What are the different options of getting 1/6? Well, the different options are, if he's only getting 1/6, well, if he gets a 6 on his first one, then we need him to not get a 6 on his second two. Brilliant, so that's one of the options. If he doesn't get a 6 on his first throw, and he gets a 6 on his second throw, then we need him to not get a 6 on his third throw. Okay, so that's one of the options as well. And the last option is that on his first throw, he does not get a 6. On his second throw, he does not get a 6. And on his third throw, he does get a 6. Now, these are the 3 different options. So this is throw 1, this is throw 2, and this is throw 3. Okay, so 1, 2, and 3. So what's the probability? Remember, these are independent events, which means that I need to multiply these. So this is why this is getting a little bit harder now. This is probably worth about 3 or 4 marks. Okay, so what's the probability of him getting a 6? Well, the probability of him getting a 6 is equal to 1 out of 6. What's the probability of him not getting a 6? Well, that's going to be equal to 5 out of 6. Brilliant. Okay, so here we want the probability of him getting a 6, which is 1 out of 6. And then the probability of not getting a 6 and not getting a 6. So 1 out of 6 times by 5 out of 6 times by 5 out of 6. So this here is the probability of getting a 6, then 2 which aren't. The next one is the probability of him not getting a 6, and then not getting a 6. So that's going to be equal to 5 out of 6 times 1 out of 6 times 5 out of 6. And the last one is not 6. So it's going to be 5 out of 6 times 5 out of 6 times by 1 out of 6. So it's getting a little bit more complicated now, okay? And then we can work these out. Now notice that these are just variations of this, okay? We could have worked 1 out and times it by 3. I'm going to work them all out. You'll see what I mean. So 1 out of 6 times by 5 out of 6 times by 5 out of 6 is equal to 25 out of 216. Now, because these are just variations of this being moved around, this one here is equal to 25 out of 216, and this one here is also equal to 25 out of 216. So these are the different options of getting 1/6. Look, there's only 1/6 in this, there's only 1/6 in this, there's only 1/6 in this, and these are the only options you can get. So then to work out the probability of all of these things happening, then what we need to do is we add these 3 together, because these are mutually exclusive events. Okay, so it is getting trickier now. So that's equal to 25 over 216 plus 25 over 216 plus 25 over 216, which is equal to 75 over 216. Super. Let's just check that answer. 75 over 216, super. Probably worth, as I said, about 3 or 4 marks that. You've got to really understand the different combinations of this. You've got to understand which one, what the probability of 6 is. You've got to understand that there's 3 different combinations, so we've got to do it 3 times. Perfect. So, I've put some questions up, and I've got 2 worksheets here for us to have a go at. So pause now and have a little go at these. I'll do the first one first. Here you go. Super, and I'll put the next one up now. So have a go at the next sheet. So pause now and have a little go at that one. Okay, I'm going to put all those answers up, so mark those in green for me. Super, so thank you for watching this video on independent events. Do make sure you're having a go at these questions, because remember, the only way to learn maths is to do it, and have a lovely day.